master student here at KTH. Emanuel has been doing his master thesis within our research lab, the Physics of Medical Imaging Division at KTH, in collaboration with the Department of Mathematics on a very exciting and totally novel technique for image reconstruction in photon-counting spectral CT. Working with Emanuel has been a great pleasure, and the only problem from my perspective has been that it has been difficult to convince him that he needs to sleep as well between his between all the time he spends doing research on this project. And so
Hello.
without any further ado, I will give the floor to Emanuel.
I'm here.
Johan, can you mute yourself?
Okay. So let's see. I'm just going to start screen sharing. Okay. Can everybody see the PowerPoint slide? Right. So thank you much for the kind words and nice introduction. It's been really nice to work with you as well, and Alma and Osan as well, the people that I've been supervised by. So the topic of today's talk was photon-counting CT reconstruction with deep learning-based physical model. So this is not exactly the same title as the thesis work, but it's a more kind of explanatory title, I think. So a little bit about me. So I study at KTH. My specialization is in applied mathematics and data science. And here is my mail if you want to contact me whenever. So the goal today, I think, is to try and present this thesis work in terms of the mathematical framework that we need. So since I am not an expert in CT, right? So there's going to be a lot more focus on mathematics today. So I think depending on the backgrounds of people that are attending today, maybe a lot of this will be repetition, but my goal is that everyone will leave this talk with some new kind of knowledge. So first I want to provide this mathematical formulation of CT reconstruction, and then we want to get you thinking about deep learning as a tool for creating physical models or learning physical models. And then by looking at the toy case, which we did in the thesis, I want to show that this seems to work. It's a good idea in some sense. And lastly, just for everyone that has the means or funding to do so, suggest new areas, kind of spin-off areas of research for continuing this topic. So more in detail, the layout today is going to be, we start off by trying to explain this title, right? Topic of the talk. So we start by looking at photon-counting CT. We move on to looking at the physics model, and we're going to explain something called the forward operator, which is an integral part of the physics model, which we're going to focus on. And then we're going to go through some theory, especially I'm going to explain deep learning and CT reconstruction from a mathematical point of view. And then we're going to go through the main method of the thesis and some results and conclusions. This is the layout, and you can see the slides, the subsections up in the top of this presentation if you ever get lost or get distracted. So since most of you are probably aware of what CT does, it's not going to be a too detailed explanation of it, but the basic idea, right, is that you have some cross-section of some image or of some object, and the property of which is given by these attenuation maps, right? So you have each of the pixels in this image has a specific property that it can absorb photons at some capacity, and you measure that in these Hounsfield units. And when you do a measurement with computer tomography, so most computer tomography setups today are based on either like single energy or some dual energy resolution, right? So essentially we're looking at black and white images. So the measurement here is going to be each pixel is represented as the amount of energy that is deposited in some specific detector. So each of these pixels represent a detector, essentially. And what photon-counting CT does is that we transition from these deposited energies into specific photon counts that are then binned into different intervals based on which energy they have. So we transition from this black and white image to a colorized version, which also allows us to think of the input cross-section here, the phantom, as a composition of different materials. Right, so we have this type of basis material separation that this photon counting approach allows us to do. So in this case, we're looking at bone, water, and iodine concentrations. And so to summarize, the thing that photon counting CT offers here is that it's a new kind of quantitative paradigm in CT, where you have much more accurate basis material separations, high resolution reconstructions, improved contrast to noise ratio, and you can, because you have these energy resolved measurements, you can counteract like this beam hardening artifact and stuff that occurs because of the fact that the photons that are deposited in the detectors are not monochromatic, or not from one single wavelength. And with this kind of new way of thinking about CT, this also means that having more accurate physical models becomes much more useful, because you want to squeeze every last drop of performance out of this highly sophisticated technology. So having a very detailed account of the physical effects behind the scanning process becomes much more useful. So these are things like scattering inside the imaged object. You have pile-up effects, and something called detector crosstalk, where the photons that are deposited in a specific detector then gets basically transition over to adjacent neighboring detectors instead. So there are a lot of different effects that you want to account for here. And on the other hand, you also want to have fast computations. You want to fast reconstructions in CT. So there's this, as I'm going to explain later, there's going to be this trade-off between physical accuracy and fast computations. So of course, there's a lot to think about in terms of physical models here, but the main focus of this thesis has been on detector crosstalk. So moving on, we're going to focus on detector crosstalk. So let's talk about the physical model right now. So we can think of these colorized sinograms and colorized phantoms as different channels, right? So each of the materials can be thought of as a separate image, and each of the energy bins can be thought of as a separate sinogram. And so the physical model that we're using here is that each of these pixels inside the sinogram is going to be a Poisson random variable. And specifically, it's going to be a Poisson random variable with a mean that is determined by this weird function here that we call the forward operator. So this forward operator takes a phantom and outputs a sinogram type object. So it's essentially a vector valued function. And in mathematical terms, we can express it as this long and unwieldy sum and bunch of integrals, but we can also think of it as a bunch of separate steps, right? So visualizing this forward operator, this large function, we can think of it as this type of network looking structure. So we start off with a phantom, and then using the ray projection, which I hope people are familiar with the ray projection, we map these phantoms onto sinograms, and then we model the material attenuation at different energy wavelengths, wavelengths. So we project these three different materials onto a high dimensional space of many, many, many different sinograms. And then the last step here models the detector response. So basically how the detectors react to different wavelengths of photons. So this last step is where the crosstalk comes into play. So if you want to add crosstalk to the physical model, essentially what we do is just we add an outer sum here that sums over adjacent detectors. So I've highlighted this as these connections becoming much wider because there's a lot more data flowing through this last connection. And that means this forward operator, when we add crosstalk, is going to be much more expensive. And in the model that we've used, it's more or less 40 times as expensive. So it's going to cause a huge load, both in terms of memory, but in terms of also computation time to add this crosstalk model to the forward operator. Okay, so this is the main problem, right? So we want accurate reconstructions, but we also want fast reconstructions. And the unfortunate reality is that there is a trade-off between accuracy and speed when we are modeling these physical effects. So if we add crosstalk, we get a very accurate forward operator, but it's also very slow to compute. And when we don't include crosstalk, we get something that is less accurate, but also very fast. So the solution here, and this is where the deep learning comes in, is that we use this approximate forward operator and try to correct it with an additional function. So this was originally, or maybe the paper that we based this thesis on is this paper here, and they use this for another type of medical imaging, but the idea is the same. So mathematically, we just essentially compose this approximate forward operator with a new function here that corrects the physical inaccuracies in this model. And the deep learning comes into play here because we let this c theta here be a deep convolutional neural network. Okay. So then we have to keep in mind why we do this, right? So the main goal here is that we want to use deep learning to accelerate the reconstruction process, but this is just a physical model. So we have to use this physical model in a reconstruction framework to evaluate it. And we have chosen to use iterative reconstruction, right? So there are many types of reconstruction. You have recently there have been deep learning reconstruction methods, and you have also there are two-step. You distinguish between two-step and one-step reconstruction methods, and I'm not going to go too much into detail to these. Just to say that we have chosen a very particular framework for reconstruction, iterative reconstruction. And so, to really understand what this means for the correction, the learned forward operator here, I think we need to delve a little bit deeper into the theory. So I'm going to try to explain deep learning from a very basic perspective, and then we're going to look at iterative reconstruction. And then the goal here is to kind of combine these two to understand how deep learning how it's affected by the fact that we're using this deep learning framework for iterative reconstruction. So, okay, so we start by deep learning, and my idea was that there are probably going to be some people in the audience who don't know what deep learning is. So I'm going to try to explain this, and I assume that most of you have heard about regression before, that you've done like linear regression. So but in regression, you have the problem that you have some data, independent data, and then you have some dependent data, and there's a relationship between these two data sets, right? You have some type of relationship that is determined by some function, and then you have some extra added noise in your observations. And yeah, so this in particular here, we've chosen zero mean noise, and then this function here is just, it maps these independent data samples onto the Y samples here. So the goal now is to try to estimate this function. And in our case, the function is just the accurate forward operator, the one with crosstalk between the detectors. And actually, since we have full access to our physical model, this noise here is going to be zero. So that's an interesting, and then raises the question, like, why would you need to do this if you actually have access to the accurate forward operator? And well, the main answer to that is that we want to do it faster. We want to kind of compress this forward operator. So in regression, the solution is just that we try to approximate this forward operator with, or this function with, a parameterized function instead. So in this parameter, we try to determine that from the data. So we try to find the best choice of the parameter. So for example, a standard way to do this is to minimize the mean square error of this function. And the process of this minimization is what we call training in machine learning, right? Okay, so to start off with a simple example, right? Because you might wonder, okay, so sure, you say that we parameterize this function, but how is this done, right? So in linear regression, the way that we do this is, okay, suppose that the data here is just a set of numbers. So in linear regression, you just let this parameter be first a matrix, which we call, I guess, the weights, and then a vector, which we call the biases. And so the way that you parameterize this function is by multiplying the input variable by this matrix and then just adding biases. And one way to visualize this is as a neural network. So we can connect all of the input variables to the output variables, and all of these lines here are represent one element inside of this matrix. So writing out the expressions for the output nodes here, we get linear combinations of the input variables plus some bias term. But then you might ask, like, okay, so linear regression is quite simple. But what happens when we want to model more advanced relationships between the input variable and this output data? And that's where deep learning comes into the picture. So let's say we want to model more complex dependencies. The linear regression method to do this would be like to try to pre-process the input data in some way. So for example, we can add these cross dependency terms right into the input data instead. And then we use that new transformed data to use to do linear regression. But what deep learning does instead is that we kind of stack these linear regression type functions on each other and separate them by nonlinear functions that we call activation functions. So this way, the deep learning kind of framework can achieve this nonlinear, highly complicated modeling by a quite simple structure. And so the more of these layers that you stack on top of each other, the deeper the network becomes. And that's basically where you get this deep learning. So if you add more layers, you get a highly expressive function, and that is what we call deep learning. So each of these input nodes are connected to each of the outputs in each layer. And that quickly becomes very cumbersome when you think about high dimensional data. So if we let this input data, for example, be an image, and you have an output layer that's also an image, then just fully connecting all of these input data to the output data here, you quickly end up with a lot of parameters. So the idea behind deep convolutional networks, which we use in this thesis, is to reduce this number of parameters by using the fact that elements are in this image are highly spatially correlated. So if you look at just one of these outputs, it's connected to all of the inputs. But what we can do in a convolutional network is that we reduce the number of connections to just a limited area of the input image. And so this is very useful when we have spatially correlated image data. And as we'll see later, that's actually the case when we use this deep learning for our physical modeling. Okay, so I think a natural question here is like, why do we use deep learning for this at all? And so, I mean, I'm going to try to answer that question, but there are a lot of different ways to answer it. So for one, as I said, the sinograms that we try to model are spatially correlated. So if we look at, let's see, here we see that there is a clear spatial correlation, like images that are, sorry, pixels that are close together are correlated. So we can use these convolutional neural networks. Let's see if I can find. So we can use these convolutional neural networks, which enables us to use these very powerful tools in deep learning. And also these deep convolutional neural networks tend to scale very, very well with image resolutions, which means that if we get good results with our toy models, then we can most likely expect these results to translate into higher resolution images as well. Then training, you might say like, okay, so, but don't we have to just run this training step, which is also very expensive? And the main point behind doing this learned correction is that, sure, training is expensive, but once we have done training once, we basically have a finished network that we can use for reconstructing any input data, more or less, given a specific detector setup. Okay, and I think a fourth point, which is really important, is that theoretically this approach could work even if we don't have access to the physical model, even if we don't know the mathematical expression for the real model. As long as we have access to real world data, we can learn the physical model anyway. And then lastly, which is a more convoluted point, but I think it's, and this explanation is going to be kind of heuristic, but the idea here is that we can use the fact that the number of possible kind of useful data points in CT are limited, and that can be used to kind of compress this forward operator. So if we imagine that this entire slide here is just a set of all imaginable phantoms, right, input data that we can get, then there's going to be some set here of kind of clinically useful data, and that term is not exactly well defined right now, and the goal is to try to define it more carefully. But you can imagine that there are, of course, there are going to be some very simplistic looking phantoms in this clinically useful data, and there are going to be some more advanced realistic looking phantoms, but there are also going to be some data outside of this domain that we're never going to see, essentially observe in the real world. And so what the accurate forward operator does here is that we can basically approximate the accurate operator. The idea of the accurate operator is that it works for all of the clinically useful data, but it also works for a lot of the data that we're never going to expect to see. And on the other hand, this approximate forward operator, it works well for a limited amount of the clinically useful data. So there are a lot of data points here that are not sufficiently well modeled by the approximate forward operator. So what the deep learning approach can do is that by training on just this clinically useful data, we can just kind of restrict ourselves to this domain, and that means that we can compress this accurate operator. Like we can parameterize this in a more compact way by ignoring the data that we never expect to see. And this is I mean, it's not a very well, rigorously stated argument, but I think it helps in reasoning why this learned operator approach can give us some sensible answer to give us some sensible physical model. But the question then remains is what is this clinically useful data, right? What does it mean? Because that's the data that we want to train our deep learning model on. So for that, I think we have to look at the reconstruction process that we're using, the reconstruction algorithm, sorry. And yeah, so let's look into that. So the idea behind reconstruction, right, is we want to reconstruct the phantom given the sinogram. And we know that our physical model predicts that the sinogram is going to be a Poisson random variable with a mean that is going to be determined by the forward operator. So one way to reconstruct it would be to find, use the maximum likelihood, basically maximize data consistency. We want to find the phantom that is maximizes the probability of observing the data that we have observed. And this is unfortunately not enough. And reconstructions, when you use this method, can look something like this. So we have something that is not physical at all. We have high variations inside this image. And we know from the fact that we have access to the ground truth in this case, that this is not a realistic reconstruction. So the solution here is that we regularize this optimization problem. And one way of thinking about that is that we transition from looking at maximizing the probability of the sinogram giving the phantom to switching this probability. So we look at maximizing the probability of the phantom given the sinogram. And most of you know this as regularization. So this essentially entails just kind of incorporating prior knowledge about the phantom, about how it's supposed to look. And traditionally we do this with just saying that these types of rapid variations here should be less likely to see in the final image. So when we do this, we get a reconstruction that is much more realistic, right? And so this maximization problem here, you can reformulate as a minimization problem by taking the logarithm and multiplying by -1. And then you can separate it out into two different terms. And this, I think, anybody who's dabbled a little bit in iterative reconstruction probably recognizes this formulation, that you have this data fidelity term and you have this regularization term. And so this data fidelity is what encodes information about the physical model. And the regularization term is what incorporates this prior knowledge that we have. And so if we want to solve this minimization problem, we're going to have to solve this. We're going to have to look like, basically it's extremely hard when we have an advanced regularization or when we have this type of data fidelity that we're using here. So the main point here is just that this minimization is hard. And what we do in iterative regularization is that we use iterative optimization methods. So we start with some initial guess, and then we use some iterative scheme to kind of iteratively update the solution until we have reached some convergent solution. So this is going to require essentially thousands of iterations, and in each of these steps, you have to compute the forward operator. So if we look back at this target function that we want to minimize, it contains the data fidelity term, which contains the forward operator. So we're going to have to evaluate this forward operator thousands of times, which makes it very expensive. Okay, so imagine now that we use this scheme here to generate reconstructions using both the accurate forward operator, but also the learned forward operator. So this is going to give us two different iterative schemes. And the main theoretical result that explains this question that I asked before, what does this domain of clinical data mean, clinically useful data mean? The main theoretical result here is that if these two gradients here are close to each other, then these two iterative schemes are going to converge to about the same solution as well. So visually, you can think of it as we start off with some initial guess. And if the learned physics model is not up to par, these two trajectories are going to diverge and you're going to end up with an unrealistic reconstruction. So you can train on this data then, this input data here, to try to align these two gradients. And you're going to end up with something that is much similar, but after a while, we still get a divergence in these gradients. So we have to train on this data as well. And we repeat this process along the iterations. So the main point here is that we have to train on not only like the resulting data, but also on all of the data along this this reconstruction process. So that answers this question that I asked here. What does this kind of clinically useful data set mean? And what it means here is that we have to incorporate all of these phantoms that appear along the reconstruction process, and not only the phantoms that we expect to see in the result. Okay, so I think this all has been a little bit confusing, but now we're going to move on to the main method, right? So how do we realize this thinking into an actual learned physics model? And I've divided the method section into 5 different parts. So we start by discretizing the spaces, and then we develop this physics model, and we formulate our reconstruction method, and then we set up a training scheme, and then we evaluate our results. So the main limiting part of this thesis was the fact that we ran all of the simulations on a personal computer, my own computer that I'm sitting right beside now. So it's only got one single GPU, and because of that, we can only use low resolution images. So for the phantoms, we used 128 by 128 pixel images. We used only 3 different materials, bone, water, and iodine. And for the sinograms, we used 128 detectors and 128 angles. So each of all the sinograms also have 8 different channels, which represent energy bins. So this is the discretized data. And of course, this is going to be non-ideal, right? This is not a realistic setting, but the idea is that we can still extract some useful conclusion out of this and pave the way for future work. So the physical model, the detector setup here, is represented in approximately 2 scale, right? You've had the X-ray tube on the left-hand side, the detector array here, and then in the middle you have the region of interest that you want to scan. And so a main thing that you might notice to begin with here is that the phantom is very small. So we're reconstructing very small cross sections here. And the reason that we wanted to do it this way and not, use a larger distance between the detectors was that we wanted to use an accurate model of this crosstalk. And for that, we have to keep the distance between the detectors constant, which means necessarily that we use the slightly too small, I guess, phantom for reconstruction. So if we expand the forward operator, this is basically the same thing that I explained. Let's see if I can find it. This expression here, but in a more detailed version. So we can expand it into 5 different components, which I've colored in different colors here. So first of all, we have the X-ray tube here, which is going to give out some spectrum of radiation. And on the left lower hand side here, you can see just the sources that we used to generate all of this data. And then we have this bow tie filter. And as you can see, I don't know if you can see it very clear, depending on which type of monitor you have, but the field of view here is quite small, which means that we're essentially using just a constant thickness bow tie filter. And then we have bin sensitivities, which model the sensitivity of the detectors to each of the different intervals of energy, photon energies. And we noticed later on that this is not exactly the correct bin sensitivities, unfortunately. So we're resulting in a model that is a little bit worse at resolving the photon energies than what a realistic setup would actually have. And then we have this point spread function, which models the crosstalk between the detectors. So this is the part where we actually get the accuracy, high accuracy. But this also comes at a cost, right? Because this is where we sum over the adjacent detectors. And in this case, we're using a proximity of 40 adjacent detectors. So it's going to be a factor of 40 times more expensive than if we're not using any crosstalk. And then lastly, we have this phantom, which is made up of different materials, and each material has its own attenuation footprint. Okay, so this is the main gist of the physical model. So the next step is to choose a reconstruction method. And here we have chosen this Frobenius regularizer, which couples materials. So if we look at the regularizer pixel-wise of this concentration map here, it's going to look something like this. So along the boundaries here, we have high penalty of the regularizer. So if you compare it to this type of less realistic phantom, you see that all of the pixels here are penalized much higher. So this reconstruction method will prefer this more smooth looking phantom instead of this high variance type phantom. And then for the optimization algorithm, we used BFGS, which is a quasi-Newton scheme. And the main point here is that we're using something that does not require the second derivative of the forward operator, because that would mean that we would have to get the second derivative of the neural network, which is not a super simple task. Okay, so we've set up the reconstruction method and the physics model, and now the only part that remains here is to actually start training our physics model. So for that, we have to have some data. So on the left-hand side here, you see the training data, and on the right-hand side, you see the data that we use for evaluation. So the training setup is basically that for each of these training data points, we simulate sinograms by drawing from a Poisson random variable determined by this forward operator. And then we use the learned forward operator to do iterative reconstruction. So that gives us a bunch of different iterates along this reconstruction path, which we then train this forward operator on. So this is just for one of the data points in the training data. And then what we do is that we repeat this process with all of the data inside of this training data multiple times until we've ended up with something that performs well. Okay. And in order to evaluate this final physics model, what we do is that we take some test phantom, we do the same thing, we simulate the measurement by drawing from this Poisson distribution. And then we generate reconstructions, but not only using the learned forward operator, but also using the accurate forward operator, the one with crosstalk, and the approximate forward operator, the one without crosstalk. And then the idea is that if this learned forward operator is any good, it should perform better than this approximate forward operator. So what we do here is that we compare the reconstructions using the learned forward operator to the reconstructions using the approximate forward operator. And as a side note here, we are not interested right now in how good these reconstructions are compared to the ground truth, only compared to the reconstructions that we get using the most accurate physics model that we have. Okay, so moving on, we're going to dive straight into the results now. So there's a table of showing the reconstruction error that I mentioned before here, these types of errors here. So I don't think it's too important, the actual measurements here, it just means mean error and maximal error. But the main point here is that the learned forward operator gives about a factor of 10, like a 90% reduction in both of these errors, which is nice. And here it's worth noting as well that the error of the accurate forward operator is necessarily going to be 0 because we're comparing it to itself. So we're only interested in comparing these two essentially. We're using this approximate forward operator as a benchmark. And in terms of computation time, you can see that the learned forward operator here takes about half of the time that the accurate forward operator takes to evaluate. So we see about a 50% reduction in computation time. And This might not seem like a lot, and that's true compared to the factor of 40 that I mentioned before. But the idea is that when we scale up this problem and use high resolution phantoms and high resolution scans, then we should see a much more drastic difference in computation time here. So, okay, so let's look at some examples of reconstructions. So here we have reconstruction using the accurate forward operator, using the approximate forward operator, and using the learned forward operator. And this is, in particular, this is the bone concentration of the image. So it's not evident that there's any difference between these reconstructions. So I think in order to really appreciate the difference, we plot the differences. So we plot the difference between the accurate and approximate reconstruction, and we compute the difference between the accurate and learned reconstruction. And then we scale up the brightness of these images. So now we can really see that there's really a difference between these two. So the error here is, I mean, about 1/10, more or less, than the error of this approximate forward operator. And the same goes for the water concentrations, as well as the iodine concentrations. And so I really want to highlight that this is a really cool result because, as I said before in the method section here, this data was the training data. So the training data is quite different from the data that we've used to evaluate the model. Basically, the bone here is on the outside of the phantom, whereas on this phantom, it's on the inside. So the training data here is quite different from the evaluation data, which is quite nice to see that this forward operator still performs well on the evaluation data. Okay, and I think, so the last result I want to show is when we rescale the measurement data. So if we change the number of detectors or change the number of views. So you see this vertical line here represents the configuration that the forward operator was trained on. And so if we scale down the number of detectors here, you can see that the learned forward operator still performs much better than the approximate forward operator. And this is also pretty interesting to see because we only trained on a fixed resolution for these sinograms, and still it performs well when you scale down the resolution. And the same goes for when you scale down the number of views here, it still performs pretty well. If you increase the number of detectors, this model becomes much worse. So probably if we want to increase the resolution of our measurements, we would have to retrain this forward operator. So yeah, I think it's safe to say that this learned forward operator works, and it's important to keep in mind that we've used it for a specific toy case with low resolutions. But in general, it seems like it decreases the reconstruction error by 90% compared to when we don't use crosstalk at all. And it decreases computation time by 50% compared to when we use crosstalk. So we really get kind of the best of both worlds here. We get high accuracy and we get high speed as well. And the idea here is that if we increase the resolution, we should see a much more drastic decrease in computation time. And then as two bonus points, it was really nice to see that it generalizes both to unseen data, but also to unseen detector setups. Okay, so finally, touching on some future work here. So of course, the main thing to do here is to try and train this physics model, learn physics model on higher resolution and more realistic setups. That's going to be expensive. That's going to, require high fidelity computational tools, which I don't personally have access to, but I imagine that some of you have. So that's a possible further work. And then one thing that I mentioned on just briefly was that we chose iterative reconstructions to use this learned operator on. But we can also imagine using this physics model for deep learning reconstruction or for any other type of reconstruction method that you can imagine. So training on those type of reconstruction methods is also a possible future prospect, right? And yeah, and another point here is that, as I mentioned before, you can also imagine correcting for other effects than just crosstalk, right? So I mentioned that there were many different type of physical aspects that you need to model in photon-counting CT. And this kind of method is essentially capable of modeling all of these effects, and even capable of modeling physical effects that we don't have we can't really express mathematically. So as long as we have training data using some detector setup, this deep learning approach can kind of learn the physical model. And the key here is that we need to have access to high quality training data. So if you are someone who's got a lot of resources and you want to employ your own, master's thesis student in applied mathematics, I think the key step that you want to prepare here is to prepare a lot of training data. And so either having access to the accurate physical model that you want to approximate with deep learning, and then generating data using that forward operator, or just scanning different phantoms with some detector setups to generate all this training data is a key step in developing this model further. So yeah, I think that's it for me, and I welcome any questions that you have, and thanks so much for listening.
Thank you, Emanuel. So the presentation is now open for questions from the audience.
Sorry, I'll start sharing again.
Hi, I'm Satish from GE Global Research. Nice presentation, nice results. Thank you for taking us through that. My question is, so you have to train at each point in the iteration. So does that mean you have a separate network for each iterate?
No, good point. No, it means that we're just using, let's see if I can find we're using the same network for the correction, but we're like including all of this data in the training set.
Okay. So you basically have to generate training set for each iteration, but then you would call all of that as one whole training set and train one global network for the
yeah. So yeah, exactly. So basically, what you do is that you I think the paper that I referenced called this recursive training. Let's see if I can find the somewhere here maybe. Right. So this part here is they refer to as recursive training. So that was the paper by Simon Arridge and Carola Schonlib from, I think they were from Cambridge. So they call this recursive training. So basically you generate reconstructions with your learn forward operator, and then you train on those reconstructions, and then you repeat that process over and over and over again. So you only yeah, basically. I hope that answered your question.
Yeah, I understood. Thanks. So can you give an idea of how much time you spent on training this?
I think so. There was a lot of trial and error, starting over all over again. So the final model that we trained, I think it was trained maybe for a week nonstop, something like that.
Okay.
And yeah, but yeah, so there was a lot of trial and error, switching the hyperparameters of the optimizer and all of that. So in reality, you would expect this to take a much longer time, but I'm guessing that if you have access to much more high fidelity computational tools, so like you can do parallel computations or GPU computing at a much more large scale, I would suspect that you can do this much faster.
Yeah, understood. So one final question about the software infrastructure use. So your training and the deep learning networks were they all on TensorFlow or similar package?
Yeah, we used PyTorch actually. So all of these
Okay.
all of these forward operators, all of the networks that we trained, all of those were implemented as PyTorch modules.
And the recon itself, was it in MATLAB or again in PyTorch?
PyTorch.
So everything is in PyTorch. So
everything
it's just,
is in PyTorch, yeah. And the reason that we did that was just that we wanted these computation times to be comparable. So it's it's possible to do this, to mix MATLAB and Python, I would imagine, but in order to get a good idea of how fast this learned forward operator actually is, we implemented everything in PyTorch.
Okay, thanks. Nice talk. Thanks.
Thanks for your questions.
Hi, Emanuel, Bruno de Man, GE Research. Very nice talk. I like how you include these image icons in between the text. One question related to Satish's question, when you retrain, when you train based on all these intermediate iterations as well, have you tried doing it without training on all the early iterations and only training based on the final kind of?
Yeah, absolutely.
Would that work? Or
yeah, it worked as well, but not as well, but it worked.
So is the end result the same, but it converges slower, or what's the difference when you do that?
So this is a little bit technical. There's some things that I haven't mentioned here. So one thing is that when you do this reconstruction step, you have to have access to the gradient of the loss function, and that means that you have to compute the derivative of the forward operator as well. So in this case, we did it with just automatic differentiation, but you can do it. You can treat the derivative of the forward operator as a separate operator and do a separate network to correct for that one as well. And we noticed that the forward operator correction generalizes very well, so it doesn't really matter that much if you use only the final reconstructions or reconstructions along these iterates. But for the correction for the derivative of the forward operator, then we really need these reconstructions along this path as training data. And I don't really know why that is the case, why this derivative generalizes so much more poorly. But it's an interesting question.
Yeah. And one more question about when you looked how it scaled to different number of detectors.
Yeah.
So it scales when you go down in number of detectors, but it doesn't scale when you go up. Is there a physical explanation for that? Is it like related to the physics of the crosstalk when you go to?
You mean why like which part of the plot are you referring to? Are you?
Yeah, just basically the horizontal axis. When you go from left to right in number of detectors, are you changing the resolution, the size of each detector cell, and you keep?
Yes. No. So what's happening is that when we change. Sorry, I have to find this slide again. Let's see. So what happens when we decrease the number of detectors here is that we decrease also the field of view, and therefore what we did is that we just rescale this phantom. So you have basically the material here is going to get a little bit thinner, right? Since the phantom decreases in size. So I think that's what explains why we see this increase. I mean, there are different ways of trying to explain it, and it will give you different answers. So the most honest answer is I don't really know exactly why we see this increased error as you increase the number of detectors. But one possible explanation could be the fact that we're rescaling the phantom to match the field of view of the detectors when we increase the number of detectors.
So it's not related to the fact that the crosstalk kernel goes in reality over even more detectors than you have modeled, and so if you increase the number, then you're not modeling the full crosstalk kernel, or is that a possible factor?
Interesting question. I don't know if maybe I don't know really how to answer that question. I do have a related plot here, which maybe can shed some light on that. So here we have, right? So the accurate forward operator that we used have like 40 detectors of crosstalk essentially, And so one natural question is like, how well does the learn forward operator compare to when we just truncate that kernel to fewer detectors? And then you can see here that this learn forward operator seems to model accurately about as well as a detector crosstalk with 20 detectors. So
I see.
I mean, that's not really related to your question, right? But it's kind of in some sense.
Yes. Okay, thank you. Nice talk.
Yeah, thanks for the question.
We have time for some questions. Yes, please go on, Lynn.
Hi, Matt. This is Lin from GE Research. Nice work. Trying to confirm that the accurate crosstalk model is like it's a 1D model, I assume, since your simulation is 2D, and like your deep learning crosstalk model operate on like the entire 2D sinogram. Is that the way it works?
That's true. That's true. Yeah, absolutely. So the crosstalk model only has like you can think of it as a 40 times 1 convolutional kernel essentially. So it's a 1-dimensional convolutional kernel, and the convolutional networks that we're using are 2D. So
I see.
Yeah, so I guess the reasoning behind that would be that you can extract some kind of you can use the fact that the shapes of these sinograms can be kind of encoded in this neural network correction by allowing these 2-dimensional kernels.
Yeah, there are some extra information that can be taken advantage of.
Yeah.
So regarding this, it seems to me like maybe a more straightforward way to train this deep learning model is to use, like, instead of embedding it in the reconstruction process, like, why not just train directly with the output from the accurate crosstalk model? So you would train it in the sinogram space instead of embedding everything in the process of iterative reconstruction.
I mean, isn't that data has to be generated by something, right?
Yes.
So you have to evaluate, in order to get to the sinogram space, you start off in the phantom space or in the reconstruction space, whatever you call it. And then you have to pick and choose which data that you want to generate the sinograms with. And that's the idea behind this theoretic part, is that we have to, the inputs that we use to generate the sinograms have to be diverse in the sense that they have to come from different parts of the reconstruction process. Does that answer your question, or do you still feel like it's
kind of, but like the training is done in the process of iterative reconstruction.
Yeah.
Right.
Yeah. Okay. So
instead of you doing that, like, what if you just try to match this phi to phi theta directly?
Yeah, that's absolutely. That's one idea. So one, okay, I guess there could be two answers to that question. For one, this accurate forward operator, when you use high resolution images, it's very expensive, right? So to generate reconstructions with that accurate forward operator might be too expensive. So that might be one reason that we want to use the learn forward operator to embed it in reconstruction instead of pre-generating all of the reconstructions, because it's much more cheap. But another explanation, and I think this was mentioned in the report, that in the paper that I cited in the beginning here somewhere, this paper, is that if you train on a fixed set of iterations, then the risk is that you slowly but surely start to diverge as these errors kind of compile or compose or summed up, basically. So the risk is that if you don't train on, if you don't embed this learned forward operator into the reconstructions and train it on the reconstructions that it generates by itself, the risk is that you get errors that kind of build up during the reconstruction process. And I wasn't able to confirm this empirically. We just picked a method and went with it. But but that's at least a possible explanation of why we do it this way. Do you feel satisfied with that answer?
Okay, yeah, thank you for your comments. Yeah.
Okay.
Maybe I can add that the point here is to that we can generate a deep learning based forward model that is very accurate approximation of the true forward model, but we can't hope to do that for all conceivable, it will not apply to all conceivable sinograms. So we have to restrict ourselves to the sinograms that are more or less likely to appear in reality when we use this reconstruction method that we have chosen.
Yeah, that was kind of what I tried to explain in this slide, right? So we have like one idea of using this learned operator is that we can restrict ourselves to only the data that is necessary for obtaining accurate reconstructions.
Yes, yes. Yeah, I guess both are options, right? You could, the training data will be always simulated from some phantoms, right, in your case. But the loss function can be either in the image space or in the sinogram space, I guess. So in your case, your loss function is in the image space.
Okay. But, yeah, actually the loss function is in the sinogram space, but maybe I didn't. Yeah, I didn't go into too much detail on the training. But the loss function is we're comparing the sinogram space loss functions. Like we are training on the mean square error of the sinograms. So we this slide that maybe I showed it earlier here.
Okay.
Right. So this is essentially what we're doing. So these are the sinograms, and here are the forward operator evaluated on a specific phantom. So this is what we're training on.
I see. Okay. Yep.
Yeah. Okay. Sorry for that.
Got you. Yep.
So it's past 5 o'clock, and I think it's time to finish the seminar. And I suggest we all thank the speaker.
Yeah.
Virtual way, and then I think that we can stay here and have a discussion with whoever is interested in asking more questions.
Yeah, of course. Anybody is welcome. I guess as everybody's thinking, I would like to take the extra time here to say a big thanks to Mats and Alma and Osan, my supervisors. It's been a really nice time to work with you, and I guess this seminar kind of marks the end of the first chapter in this journey. So really appreciate it, and also of course appreciated the opportunity to come here and talk with you guys. Really nice. So thank you for that.
Okay, thanks for listening today, taking part in this seminar, and thank you, Emanuel, and welcome back to MedTechLabs Seminars. Bye.
Bye, everybody.
Thank you. Bye.
Thank you.